would be good to know with regard to chemistry. So things that you maybe learned, oh, did I give you this yet? Okay, good. Things that you maybe already learned in grade school was that all matter has weight or has mass. Those are two different things, but all matter has mass and occupies space. And basically matter is made up of cute little atoms. I just love it. I think they are so cool. So the atom is the repeating unit of matter. And I just gave you a periodic table to tell you the different kinds of atoms, elements, or atoms, different kinds of elements. Okay. So it's not a new idea. Clear back, Democritus, clear back in 470 BC, thought about this idea of an atom. The word atom means that it remains intact. Now we're going to kind of take up atoms. This is water, so what atoms are making up a water molecule? H2O, hydrogen, oxygen. So that's all this is saying, is that atoms stick together in a repeating unit, in this case a water molecule. Okay, so it's very cool. So what is NaCl? Salt. It is salt, yeah. Table salt, sodium chloride, exactly. You got it. So this actually kind of says, where did the word atom come from? So now in here it says that an atom can't be divided. An atom can't be divided. Well, actually, now with nuclear, we actually can take, we can split an atom. We're splitting an atom, so in that case, an atom can't be divided. Now, atoms that split quite well actually are things that are above iron. What's the symbol for iron? It's got two letters. Fe. Symbol for iron is Fe. Very good. So things above iron actually kind of do pretty good splitting. Okay, things below iron do good putting them together, which we call fusion. This actually, I know it's small, but it's not small because it's not important. Actually, this is kind of important. That there's this logic tree sort of thing. So matter is made up of atoms. Matter has mass, occupies space. Matter can either be a pure substance or it can be a mixture. Okay, and if it's a let's go this way. If it's a pure substance, it can either be an element. So all element means like as if I had a chunk of carbon here. All of those would be kilocarbon atoms. It can either be an element or it can be a compound, like compound, water. Here, with regard to mixtures, we can have a mixture that this is two or more substances that are tossed together. Okay, and we can have it homogeneous, means it's like really homogenized, the same throughout. We're going to have heterogeneous, where it's non-uniform. It's what we call chunk. So all matter is made up of atoms. Okay, as mass occupies space. So let's see a little bit kind of what an atom looks like. Now atoms are very small. I actually have a video to show you to kind of get a sense for how small atoms are. But atoms generally have this structure. We're going to talk about three pieces of an atom. Do you remember what I told you a minute ago? So like, what is that whole number for helium, for instance, 2? That means 2, there's letter P, protons, 2 protons. Yeah. So protons and then neutrons, and they're both in the center. Protons in the middle, neutrons in the middle, kind of hugging each other. We have electrons outside. We'll talk more about the electrons. So this is kind of what we have going on. Protons and neutrons in the nucleus, and electrons in the cloud outside. So the electrons are actually where most of the energy is. We're all tired here. We're like, let's get do things. Okay. When it comes time, especially speaking of electrons, when it comes time for the subatomic particle to have the motion, the electrons are negatively charged, and electrons basically they don't have mass. They're what we call masses. They're very light compared to the other two subatomic particles. Protons are positively charged. Protons, we're going to talk about how do you weigh an atom. Are you serious? Well, we're going to use the symbol U, which means atomic mass units. I think it's at the bottom here. Atomic mass unit, the symbol U, that's what we use to weigh an atom. How big is that? How big is an atomic mass unit? Well, 1 gram, which is mass, would have 6.022 times 10 to the 23rd atomic mass units. Small. So like I said, protons are in the middle. Now, the protons, as it turns out, is what tells you what atom you have, what the identity of the element of the atom has. So for instance, if I said, here's your periodic table, guys. If I said I had 92 protons, what element do I have? I do have uranium. Ding, ding, ding. Very good. But other periodic tables actually say that anything heavier than uranium, that's a lot of elements, actually is man-made. It's what we call synthetic. It's no longer naturally occurring on Earth. Maybe it was there before, but it's what we say unstable. It's broken down into something smaller. So anyway, uranium, 92, great. So the number of protons say what element it is. What else we have? Now, there are some terms in all the different things you take in college. And with regard to chemistry, the term atomic number is an important one. So atomic number is the number of protons in an atom of an element. And so what is the atomic number for carbon? 6. Very good. What's the atomic number for, what's the symbol for silver? It's 2 letters. It is Ag. Yep, symbol for Ag. Atomic number 47. You got it. Perfect. Let's say that. I guess that's what I was going to say. What's the symbol for gold? AU. I know, it's like, I get those, I used to get them mixed up. I'm doing better. Yep, AU is gold, AG is silver. All right, so protons are positively charged. They're the atomic number. They're very important. Okay, electrons are important too. Neutrons are important too. They're all important. Neutrons they have no charge. So actually, electrons, we kind of do an E with a superscript negative. Protons, a P with a superscript plus. Neutrons, an N with a superscript 0 because they're neutrally charged. They're also in the nucleus, and they actually help kind of dilute the protons that are in the nucleus because like charges repel other like charges. So with all those protons, if you pick on, who would we pick on? 47 protons in the center of a silver atom, they wouldn't want to all be there. So the neutrons kind of help them chillax, relax, and all kind of smooth the nucleus of a silver atom. So we said the electrons are light, basically massless. We said the protons weigh about 1 AMU, or 1 atomic mass unit, 1 U, and actually the neutrons weigh about 1 U also. Now, one of the things I didn't mention yet, but it's going to come up, so if electrons are negatively charged outside the nucleus, and protons are positively charged inside the nucleus, here's the deal. If we pick on silver, 47 protons, if silver is what we say no charge, if the silver atom has no charge, well then those 47 protons have to be counteracted by 47 electrons outside the electron cloud, and they do. If you're talking about silver atom, no charge, 47 protons, 47 electrons. That's just what it does. Now, the silver atom actually can quite easily kick off one electron, and then actually now it's not neutral anymore, but 47 and 47. All right. So here is a little video on just how big is an atom. Volume of a nucleus versus the electron cloud. So Neil deGrasse Tyson had kind of revisited the Carl Sagan Cosmos series a few years ago, and one of his episodes he talked about, I don't know if it's a chemist or a physicist that came up with this idea of, oh my gosh, an atom is mostly empty space, and it was said that he got up in the morning and he was afraid to step on his, he was afraid that he would fall from his floor. Actually, the floor is mostly empty space. So the way it works, and this is kind of mind-boggling, is the reason we don't go through the floor has to do with the electron cloud of the flooring material versus the electron cloud in our beams. So it's like electrons, they will mix. So covering. I know. Also, I heard that we've got the Olympics coming up, and did you hear that? Like the people that first did ice skating, like the first skates were like 2000 BC. First people did ice skates. Skates are really cool things. They blade, apply pressure, they put on the ice. Anyway, pretty high tech. So what I started to say is, if you take the nucleus is the size of a BB, what the slide tells you then is that the closest electron would be like 5 stories from it. So. One of the things your textbook talks about in chapter 9, and I'm going to kind of hold you accountable for, is how do we, over the years, how we come to know what kind of the structure of the atom we now know it to be. So, for instance, back in 1803, Professor Dalton, I guess he was colorblind, but anyway, Dalton kind of revisited this idea that matter is made up of these little things called atoms. So there's his atom. And then in 1904, Thomson came up with this idea, well, atoms, they actually have positive and negative charges in them. But did Thomson know about the nucleus? Sometimes that's called the bread pudding model, because he just had this kind of all over the place. Now, Rutherford, the reason you kind of see this dark purple here, is that Rutherford came up with the idea that actually the pluses and minuses aren't just like a homogeneous mixture in the atom. The pluses are concentrated in the nucleus, and negatively charged particles called electrons are kind of outside. So the light purple is where the electron, what we call electron cloud is. So now we're getting kind of like, think of an atom. Okay, this one always reminds me of like a Tootsie Pop. How many licks does it take to get into the center? So that's Rutherford's model. Now, Bohr was an important step from Rutherford. The difference between the Bohr atom and the Rutherford atom is these little balls right here are supposed to be electrons. It's not drawn to scale like the guy said. But these electrons now actually have specific what we call energy levels. So instead of electrons kind of being willy-nilly out here in a cloud, electrons are very organized. So electrons can be here at what we say a lower energy level, closer to the nucleus, or electrons can be here at a higher energy level, farther from the nucleus. And then Schrodinger, I'm going to go ahead and play you this song that's totally annoying, so I apologize in advance. It kind of talks about these people. But Schrodinger again said, all right, we have the positively charged nucleus, the protons and the neutrons, and the electrons are outside the nucleus in these different energy levels. But he said kind of the ... he said, it's really hard to know exactly where they are. Bohr said we can know exactly where they are. Schrodinger said no, you can't. So if you kind of see a picture drawn like this, it kind of makes me itch, where it's not that, for instance, if this was a silver atom with 47 protons and 47 electrons, it's not that this represents 40, these little dots, there's 47 dots. It says that those 47 electrons can be here, here, here. They're just kind of trying to show you kind of the clouds are things. So yeah, here's the song I was telling you about. Here's why we're different. So I went ahead and I don't know if we'll get into this too much. We might, but I went ahead and gave it 3 protons, obviously, because it's atomic number 3, 3 electrons, because I'm like, hey, it's probably neutral. And then with regard to neutrons, excuse me, I looked at its, what I call its decimal number for lithium. In the box for lithium, we have 6.94. And I kind of rounded 6.94 up to 7. About 7. So if that's kind of how much how many U's it weighs, 7. So I'm like, all right, well, if it weighs 7 U's or so, if my protons are 3 U's, that means I must have about 4 neutrons. That's kind of how I came up with that. That's just a very ballpark thing. Any questions about all that? Good job. Okay. So, electrons, starting with Bohr and then on with Schrodinger, they said that electrons aren't just willy-nilly, they are actually have certain energies. And a good way to show certain energies, well, first off, I guess I already showed you a minute ago, if we have the closer the electron is to the center of the atom, we call the nucleus, the lower the energy. So I saw in some of you guys' things you had, I'll just put N for nucleus in here, and then you guys had kind of the energy levels here. So I like that some of you put 2 electrons here, very good, and then maybe the 3rd electron right here. So, and that's cool, actually, there is definitely some validity in all of that. So these have lower E, and these 2, and this guy has higher E. Okay. And there are definitely rules. There's like a capacity, like for shell, like energy shells, how many electrons you can have. So here's the deal. In that way, we say that all this is showing you is kind of what we call quantity means amount. Quantity means amount, like how many you got that you give me your quantity. So quantized means a certain amount. So we have this sort of step sort of thing. If you think of, for instance, this is kind of the nucleus of the atom, and you can kind of see that it can go be an H1. H1 might correspond to this guy. This might be H2, H3, H4, but we're just talking about different, okay, farther from the nucleus, different levels of energy that electron can be. So that's what we say quantized. The energy is quantized. Again, with Bohr, he said that, Schrodinger said that, we know that in the case. This is not quantized, so a ramp is not quantized. Stairs is quantized. So, excuse me, this is a look at some different energy levels, and there's kind of some subdivisions within these principal energy levels, but we kind of have this energy level N is equal to 1, energy level N is equal to 2, and you kind of see these kind of concentric circles. So I'm actually kind of, the reason I chose this topic to talk about chemistry isn't just to be cruel. It actually relates to when we talk about astronomy. It's going to link in. So one of the things that electrons are great at doing is you can actually zap them with a little electricity energy. It doesn't have to be electricity. You can zap them with energy. So this red thing is zapping. Okay, I like these figures from your textbook. And then you can see what happened to that electron. It was there, and now it's there. What would you say? It moved. It jumped up to a higher energy level. Yeah. And I've got a friend who teaches chemistry in high school, but and her kids just love this, you know. So you give me a little bit of energy, and I'm an electron, and I'm going to jump up to a higher energy level, you know. So she gave me energy. And then as it turns out, as I jump down to a lower energy level, I'm going to give off energy. Okay. So we call this absorbing energy, a photon of energy. Now, there actually is some cool visual things that we can do. I'm looking up at these light bulbs here. Do you guys know that light bulbs actually have a gas in them? Because if you break a light bulb, it doesn't work anymore. And that's in most part because the gas has escaped. The way light bulbs work is that basically they have a little filament, okay, that can provide electricity to the gas inside. Okay. So the glow actually occurs as the glow actually in a light bulb occurs as the electrons fall back down and they emit it. They take energy from electricity and they emit light, okay, as they fall back down. So they take energy from electricity as they fall back down, they emit light. That's convinced myself of that. Now, there are some cool things that happen with regard to elements. In this little experiment, I've got hydrogen gas there. What's the symbol for hydrogen? What's the letter symbol? H. Yep, H is hydrogen. So the thing about if you have, not light bulbs too, but to a more extent, if we just had a hydrogen light bulb or a hydrogen gas, what it would do because of its specific electrons is give a fingerprint relative to hydrogen. How if a hydrogen atom is neutral, how many electrons is there? How many protons is there? What's its atomic number? 1. Yep. So it's 1 proton and it has 1 electron. So what happens, and it's kind of like a DNA fingerprint. Actually, we can see that 1 electron kind of transitioning, and it will give, it's kind of, you can't see the whole thing. Just get rid of this. It will give a fingerprint. Can you see this kind of fingerprint over here? This fingerprint is right here. I see 1, 2, 3, 4. I see 4 places where the hydrogen electron has sucked up energy at those particular 4 energies of color. It's a fingerprint. It's a fingerprint for hydrogen. And I said this is where it kind of intersects with astronomy. That's how we know that there's hydrogen out there. We can see hydrogen's fingerprint. Well, that's absorption. Okay. Now, this case, this is what we call already an excited electron. It's so exciting. Okay. And it, like I step down from the chair, it's actually going to give off energy. Okay. It's energy escaping. And then as it turns out, we picked on hydrogen again. When it gives off energy, it gives these same 1, 2, 3, 4. It gives those same lines, but now it's giving it off instead of sucking it in. Okay, so it's giving up 1, 2, 3, 4, 1, 2, 3, 4, but in this case, it's letting it go. This is what we call an emission. Energy is being emitted. This is what we call an emission line. So fingerprints. Hydrogen, helium, carbon, helium, iron, calcium. What's the symbol letters for calcium? 2 letters. And actually, they're the first 2 letters. Ca. Calcium is Ca. So these are actually what we call stellar spectra. These are like fingerprints of the stars. And if you know what you're looking for, these lines that scientists have marked in there are those elements on those stars. The other thing about this is, can you see, for those of you who had any astronomy, you can see the O, B, A, F, G, K, M. These are different types of stars, where this guy's the hottest up here, and this guy's the coolest down here star. Well, actually, I see over here. What does K stand for here? Kelvin, yep. This is the temperature in Kelvin units, yep. So this is the hottest stars, this is the coolest stars. These are their fingerprints. Do these look more like the first when we saw helium, dark lines, or do they look more like the second one, bright lines? The first one, yeah. These would be absorption spectra. Well, back to Earth a little bit. Fireworks. Who doesn't love fireworks? Right there. It seems like they are adding new colors. I don't know. But the color of the firework is a specific energy related to the electrons around the atom that they're exciting up there in the air. This is so cool. It emits light at a certain energy. Okay. So that's how fireworks work. And so actually here you can see kind of chemistry of fireworks. The white ones are magnesium, the red ones are strontium, the blue ones are copper, yellow sodium, violet are strontium and copper. Oh, they just keep getting better and better. Another place where we have this sort of emission of light because electrons were excited is this, where it's on my bucket list to see, anybody who's seen some good northern lights or southern lights? The way they work is you have to be, we're a little bit south of the North Pole to see them. But if you get closer to the North Pole, as charged particles from the sun overload the Earth's atmosphere, they fall through. So if you have an overly active, we'll talk about this in astronomy, but if you have an overly active sun, you can actually get, Earth's atmosphere can't hold all of those charged particles from the sun, and they'll eke in at the poles. And that gives us our northern lights. And as they eke in, electrons are excited, and they glow up like that. It's so cool. Well, I kind of finish up with the next slide is just a big old question mark. So Schrodinger's model, that was the most recent one, right? And Schrodinger's model was kind of related to Heisenberg's uncertainty principle in that when it comes time to find where an electron is, you really can't narrow it down as good as Bohr said you kind of did. Bohr's model kind of looks like, and we still think of Bohr's model when we draw pictures, but it looks like our solar system. Bohr's model looks like the sun in the middle, which is the nucleus, and then the electrons kind of orbiting, and that's not how it works. So Schrodinger kind of came up with this sort of the itchy sort of electrons. Itchy. This is the nucleus, the blue dot, and then kind of this cloud-looking thing are where the electrons, the probability of finding an electron or two. Okay. Now we like to think of as kind of, we like to, and we follow it quite naturally, we like to think of atoms as being circular okay, where you have the nucleus and you have the electron cloud being circular. That's not necessarily true. So they kind of have some interesting shapes. For instance, this would be our circular sort of electron cloud. These dumbbell shaped, very, very common in how the electrons go around. The nucleus would be right there, nucleus right there, nucleus right here. In the spherical, we have the nucleus in the middle. And then we have this other sort of shapes where the nucleus is there. And kind of those dumbbell shapes are where electrons hang out. So Heisenberg's uncertainty principle, excuse me, it only kind of works on very small things, kind of like electrons. Heisenberg's uncertainty principle doesn't only apply to we're uncertain where the electrons are, but it does. Okay. So, this will be due on Wednesday. I'll bring in the next part for chemistry on Wednesday for lunch. In the meantime, let me know if you have any questions. Good luck studying. Check out that Ed puzzle video. It's not too bad. Hmm?